All right. Okay, there we go. So shouldn't have an issue with the recording today since we're not using my laptop. Um, so a couple of things I want to mention before we get going. So you've got that problem set. In fact, I think I have it up there right now. I'll create an actual assignment link where you can submit that. We should be able to, after today's class, work all the way through the last question. So we should be able to get through everything today. For that quiz, that second quiz, we probably won't cover the last question on the quiz until Tuesday's class. So what I'm going to do is open that up after Tuesday, and we'll be set to be due at the end of Friday. Okay. So after today, you'll start to be able to review every single question that you'll see on that quiz, with the exception of the very last question, which we'll cover at the very beginning of Tuesday's class. Okay. So a due date for the quiz is going to be at the end of next Friday. So I'll get that kind of updated. That problem set, I'm going to update to be the end of next Friday as well. Okay. Once again, you should have everything you need to kind of answer that problem set after today. There's a chance maybe we don't quite get to something at the end of the class. We'll cover it the first thing on Tuesday. So start getting, start working on getting the vast majority of that problem set done as soon as possible. My office hours next week, I'll kind of let you know in advance. I have an exam in my B251 section, so they'll probably be a little bit busier. I'll try to change them a little bit so I have additional office hours just for you guys, so you're not kind of competing with them. And my office hours Wednesday are likely going to be a little bit later in the day, so probably in the afternoon instead of the morning. Okay, so it's kind of making you aware of those changes. Other than that, I think that should cover everything before we kind of just dive into material here today. So any questions for me before we get going? Okay. You got to speak up. Yeah, speak up a little bit. So I have them all graded. I'll get them posted after class today. I was kind of waiting on a response from one person that had a corrupted file, but I'll get those problem solutions up so you can kind of go through and see what the code should have looked like. But they're all graded as of yesterday. Yep. So I'll get those set to be released later today as well. So thank you for asking that. Any other questions before we get going here?
When is the quiz?
So when is the quiz and problem set due?
Oh, yeah.
Next Friday at the end of the day. Yep. So I'm going to get those updated after class today. Want to make sure I mention them before I start playing around with dates. Okay. All right. So where did we leave off? So we started talking about kind of simple linear regression, making interpretations of the coefficient, slope, and intercept, determining if it's statistically significant, being able to do kind of rejections using hypothesis testing. Just like we could with sample means, we can also build confidence intervals. Okay, so I'll kind of show you how to think about this in relationship to what we've already talked about. So when we're looking at a sample mean, how did we build a confidence interval? We kind of took however many standard deviations away we needed to go to get our desired alpha total in the tails. So we had two-tailed tests. That was going to mean whatever z value would give us half of alpha in each tail. Okay. What we're going to call this, that I wasn't really referring to it as before, but especially when we look at regression, we're going to call this our margin of error. Okay. The thing that we're adding and subtracting to that sample statistic is our margin of error. So we said, if instead I want to build a confidence interval for my slope coefficient from a linear regression, I'm going to go a certain number of standard deviations away. That gives me half of alpha in each tail. We said we were always doing two-tailed tests, right? We were always assuming the coefficient was equal to 0. Can we say that it's not? Now here, instead of this kind of standard deviation, we had a slightly different term, which we called it. This is the standard error of your slope coefficient. You can think of it like a standard deviation, because we said kind of what is this equation? So it's like the sum of our errors squared over n minus 2 over something else I told you not to worry about, right? So we can kind of think about this really very similar to this represents, right? Oh, n minus 1. kind of represents almost like the standard deviation of our slope coefficient, okay? So we can use the z values to approximate what gives us half of alpha in each tail. What Stata is actually going to do, because it'll report the confidence intervals to us, I think I showed this to you last class, is it technically uses the student t and can correctly identify. It doesn't have to approximate. So the confidence intervals we get, I can ask you to construct them. If I do, you can just use those standard normals to approximate. When you actually run the code, it can be more precise. Right? It doesn't have to use those standard normal values to approximate. It identifies the correct student t distribution. Okay. So we said, kind of, what are two things that are going to change this confidence interval? If the sample size goes up, it's going to happen to this fraction. Denominator is larger, so it's going to go down. So our confidence intervals from that are going to get narrower, right? And we think about a confidence interval, it's telling me with this amount of confidence, the true population coefficient is somewhere in this range. Okay? If we're assuming that it's 0, maybe at this kind of sample size, I can't reject, right? 0 is one of the possible answers. But when I get a larger sample size, maybe now my confidence interval is much narrower. Now 0 is not in it. Now I would be able to reject that as one of the true possible population values. Okay? Same kind of thing would apply if I want to say things with a, excuse me, higher level of confidence. What's going to happen to alpha? So 90 versus 99% confidence, alpha is getting smaller, which means the number of standard deviation of the way I need to go to get that desired alpha is going to go up. So when I want to say things with higher levels of confidence, that's going to make my confidence interval wider. So now there could be instances where before my confidence interval didn't include 0. With a higher level of confidence, maybe now it does, right? It makes it harder for me to reject the null at higher levels of confidence. So this is very similar to what we're doing with the sample mean. It's just now we're doing it for this sample slope coefficient. Okay. Any questions on this idea before we keep moving? So those are really the two things that I'm going to kind of focus on or expect you to know about what changes the confidence interval: the sample size and the confidence level, or essentially alpha that we're selecting. Okay. So we go back here, right? If I'm looking at some Stata output, it tells me the 95% confidence interval by default. Okay? So in this example, is 0 included in my confidence interval? So it could be one of the true values. So am I going to be able to reject 0 as a possible true value? No, right? In fact, if I did a hypothesis test, we won't often do this, but if I said we're always going to do it, is it equal to 0? If I wanted to say, is it equal to 100, could I reject or fail to reject that? Is 100 in my confidence interval? Yes. So could it be one of the true possible values? Yes, I would fail to reject. What about negative 200? Outside of my confidence interval, it can't be with 95% confidence one of the true values. I could reject that. Okay? So that's kind of what we're doing with our confidence intervals. Just to kind of give a different example, let's say I have that different data set. I'm now looking at my 95% confidence interval. Can I say with 95% confidence that the number of days someone uses marijuana each month impacts their predicted income? So what value would mean that there's no effect? 0. Is 0 in my confidence interval? No. So I can reject that as a possible true value. I found that there's a statistically significant effect of the use of marijuana on predicted income. The test statistic and p-value, that approach would tell me the exact same thing. So we can really make rejection decisions using the test statistic. Is it larger than my critical value? The p-value, is it less than this alpha that I set? Also, is 0 in my confidence interval? If it's not, then I can reject it as a possible true value. Now, what would happen here if I wanted to instead do the 99% confidence interval? So if I want to say things with a higher level of confidence, I'm going to need to make my interval wider, right? So if it gets wider, is it more or less likely that I can reject 0 as the true value? Well, if it gets wider, what's going to happen to this upper bound? It's going to get closer to zero. Potentially, it could go past zero. Now, I don't know unless I do the actual calculation, but it is going to make it less likely I can reject, because it's going to make it more likely my confidence interval, as it gets wider, it's more likely it includes zero. Okay. So here, it's not in my interval though. For 95% confidence level, I would fail to reject. Yeah.
Do we always test for zero for the interval?
What did I say? The null hypothesis for our slope coefficient always is. We assume that it's equal to zero. Yeah. But if we did want to say our other values, could I do a hypothesis test for negative 100 here? Yes. If I look at the confidence interval, the test statistic and p-value always tell me, or always use an assumed true value of zero. But with my confidence interval, any assumed true value in this range, I would fail to reject. Any assumed true value outside of this range, we're primarily focusing on zero, but I could say negative 100, it's outside my range. So if I did a hypothesis test for not being equal to zero, but equal to negative 100, I would fail to reject. It's not a possible true value because it's not in my confidence interval. Okay. Any other questions on this idea? Okay, so we kind of talked through the significance, statistical significance. Along the way, we'll start to talk about economic significance. Even if I find a statistically significant effect, if it's relatively small, I might not worry about it, right? I mean, if I'm thinking about here, if this was like annual earnings is a loss of $250 for every day to use marijuana, that much? No, it's not the highest economic significance. It's statistically significant, right? But it's a relatively small value in terms of the percent of someone's income that it would be. Okay. So kind of then start to think about how we do this in Stata. So I showed you a little bit last class. I'm going to open up that regression in class kind of file, do file that I had up on Canvas. Here is my global path. Yours is going to be just your OneDrive, whatever you kind of have it set up to be. So we're going to go down here and use this COVID county data. Okay. So I'm going to open this up. Make sure I have the right file path. Maybe I didn't. Let's see. That's probably why I put the global path in here. What is it not liking? Oh, I moved this to week 4, probably. Yep, sure enough. So once again, just review because I forget where I put these folders or files. If you ever forget what folder you put it in, go to that folder, open up the data. Everything before the file name, that's your file path if you start to use subfolders. So I'm just going to copy this, go to my do file. I moved the files around, so I changed my file path. It wasn't in week 3, it's now in week 4. All right. So now I should hopefully be able to open this up. I think I did this last class, forgot to save it. So I can kind of start to look at this COVID data and run some simple linear regressions. We talked about scaling the variables last class. So I'm going to come all the way down here because we haven't talked about R squared yet. I'm going to go up here. So I think it's what, line 166. I would not expect you to do something like this, but it's once again, I will sometimes show you the power of Stata and try to prove some things that I'm telling you with some actual data. Okay. So I'm going to use that COVID county data, which I already opened up, and I'm going to run this regression where I try to predict the number of cases per 1,000 people with the percent of the county that was vaccinated. This is an example we looked at last class. Okay. So I run that. I get my regression output. The true coefficient, or sorry, my sample, this is population data, right? So the true coefficient, I don't have to worry about, I don't have sample data here. I know this is the true effect of getting a 1 more percent of your county vaccinated. I also know this is going to be my true standard error because I'm working with population data. So I'm going to use these 2 values, right? I'm then going to think about, okay, what if instead I took a bunch of samples from this population data set? Now in practice, we usually only have 1 sample data set. That's all we can make our decision on. But if I start to take a sample from the population data, and let's say I do this 1,000 different times, I run the regression, I'm going to have 1,000 different sample coefficients that I come up with. What should they be centered around? just like the sample mean, if I take enough samples, the distribution should be centered around the true population mean. So my sample coefficients, if I take enough samples, should be normally distributed around the true population coefficient, which we said we had the population data originally. We know it was like what, negative 0.25. Okay. So I'm going to randomly sample 1,000 different times samples of size 30. I'm going to run this regression, save that sample coefficient. So I'll have 1,000 different sample coefficients. Okay. So that's what I'm doing with this program. I would never expect you to kind of know how to code this up, right? But I'm going to go ahead and do that. So I now have 1,000 different sample coefficients. If I summarize this, the mean of those sample coefficients should be whatever that true population coefficient is, right? The distribution should be centered around that value. Sure enough, what is the mean of those 1,000 different sample coefficients? Negative 0.25. Now it's going to be a little bit off because if I really had to prove this to you, I'd have to have like an infinite number of samples, right? Which isn't, you can never truly prove it to yourself with data. But if I start to take higher and higher number of samples, it would get even closer to that true population value. Okay. Now, what's going to be true about kind of my standard deviation? So if we go back up here, or my standard error, I should say, sorry. My standard error is going to be different than what the population standard error is. Why? Because that kind of got scaled. Remember, the sample size was in that calculation. So when I was dealing with population data, I had much larger sample sizes, which made my standard error a lot smaller. Here I only have samples. I don't have the population data. I've only got samples of size 30. Okay. Now, if I do a histogram of those coefficients, hopefully they're not only centered around the true population parameter. We're waiting. They should be fairly normally distributed around that true value. Okay, of what? Negative 0.25. Okay. And this gets to be even closer to a normal distribution if I was to take higher and higher sample sizes or have more samples. I can do the exact same thing. If I do this from samples now of 100, what should happen to that distribution? So it still should be centered around that true population value of negative 0.25. But what's going to happen to my standard errors? When I increase the sample size, we said the standard error is going to go down. So now if I look at this distribution, if the standard error I can think of as like the standard deviation, my distribution is going to become a lot more peaked, right? Or it's going to be narrower. So originally, this is where we can prove this to ourselves with data. Here was when I had samples of size 30. I'm seeing some samples of like 0.5 and negative 1. When I do the exact same thing, but take higher samples, those extreme values should be a lot less likely, right? I should be getting a more peaked normal distribution. So I'm going to go ahead, run this, take 1,000 different samples of size 100 now. What ends up being true is if I summarize those coefficients, they're still centered around that true mean of negative 0.25. But notice what has happened to kind of that standard deviation or the variance in those values. It is now, instead of 0.23, it is now 0.12. It's a lot smaller. If I then look at the distribution, it should be normally distributed around that true value of negative 0.25. But notice, I'm not seeing values as high as 0.5 and negative 1 now. The most extreme values I'm seeing are much smaller in absolute value, right? So I'm getting a narrower distribution, or just like we talked about, if I take higher sample sizes, I get a narrower confidence interval. And I'm making it more likely I can reject. Okay. So we can prove these things to ourselves with data. Just because we were talking about confidence intervals, if I had those same samples of size 100, I'm just going to have some code here, where basically I create my lower and upper bound. So for each one of those samples, I take that, where am I at? I take my sample coefficient. I would then add and subtract that margin of error. So the margin of error was the number of standard deviations away we needed to go to get alpha over 2 in each tail. Right? So the value for the 90% confidence interval is going to be about 1.65 or 1.645. I'm then going to multiply that by, and I kind of calculated this standard error. So 0.126 looks like here. Every single time I run this simulation, these will be a little bit different. But that was my kind of standard deviation of those coefficients. If I create my upper and lower bound, I then create a variable that says, is that true population value somewhere between my lower and upper bound? If it is, put a 1 in here for this variable. If it's not, put a 0. So 90% of the time, because that's the confidence interval I was building, my confidence interval I create should include that true value of negative 0.25. All right. So if I go ahead and run this and then summarize this, hopefully, what's the mean of that 1, 0 variable? That's just the proportion of times my confidence interval included that true. It's close to 90%. Right? It's always not going to be exact because we're dealing with only 1,000 samples, but it's going to be very close to that. Right? And then if I wanted to instead say this with a higher level of confidence. So let's say instead of 90%, I wanted to say this with 95% confidence. Well, if I want 95%, that means alpha is going to be smaller. So to get less area in my tails, I'm going to have to go a higher number of standard deviations away. Instead of 1.65 approximately, the values that we would get are going to be, or kind of our critical values, are 1.96. So if I then do the exact same thing, I have to run this again because I've created these variables. Now when I do this, we're waiting. Hopefully now, instead of about 90% of those confidence intervals, including the true population parameter, now I get about 95. Once again, it's going to be a little bit off because I only have 1,000 samples, right? And I'm rounding things to like the 4th decimal. But we can kind of prove these things to ourselves with data. Okay. Any questions over anything? Once again, I wouldn't expect you to kind of run these programs. I'm just trying to show you the power of what we can do, and also that what we're saying theoretically is supported by the data. Okay. Now, in practice, we only ever have usually one sample. Okay. So we're then going to kind of start to talk about something else that we can get from our samples or from our sample data from this regression output. So it's going to be called the R squared. Okay. So all an R squared is going to be the ratio of how much our regression model, this regression we ran, how much of the variation in Y is explained by the predictions we're making. So when we came up with a predicted Y, we said it's whatever our slope and intercept coefficient are from the regression. So the kind of a reminder, if I can hit this right, there we go. Okay. My predicted Y values will simply be that intercept and that slope estimated coefficient I see from the state output. And then for every observation, I'll take that observation's X value and make a prediction for what Y is. So our predicted Y values will be how much of the variation in that we could explain in the actual Y variable using our predictions. Okay. Now, that is going to be what we call the explained sum of squares, right? It's how much our predictions vary from the mean. Right? Then we square it to penalize like really bad errors, just like we have for the variance, things like that. Now, the total sum of squares will be the total amount of variation that exists in the actual Y values. So here's like the total variation that exists. Here's the amount of variation our predictions explain. The ratio of those two, R squared is going to be kind of in decimal form. If we had an R squared of 0.8, that means that we can explain 80% of the variation in our Y variable using our regression model, right? Or using our predicted slope and intercept coefficient. So R squared is always going to be in like decimal form. So the probability we can explain would be 0.8, which means we can explain 80%. We had an R squared of 54. So, or sorry, 0.54. That would mean we're explaining 54%. Right? So we can always kind of just, usually when we see R squared, the way it's reported in Stata will be in that decimal form. If we ever want to say like what percent of the variation can we explain, we just multiply by 100, right? Going from a probability to a percentage. Okay. So if we're looking at some output, so I'm going back to that births and shale well example. What percent of the variation can I explain? 0, right? And think about why that's the case. If I can explain 0% of the variation, what would it mean? That X variable is not a good predictor of Y. If it's not a good predictor of Y, what should be true about that null hypothesis that the coefficient is equal to 0? It means that I can't explain much of the variation in Y with X, then the coefficient on that X variable should be 0 essentially, or I should be failing to reject the null. Here, we failed to reject the null a lot. The p-value was 0.96, right? We weren't even close. So when we end up with these really high p-values, what that's going to suggest is the X value isn't a good predictor at all. The R squared tells us a very similar thing, right? When we have a very bad predictor as our X variable, the percent of the variation our predictor can explain of the variation Y is going to be really small. In this case, it's very small. It's 0, right? Now, this will make a little more sense when we move to future topics. When we start adding in variables to our regression, it'll get a little bit more complicated, and then we'll kind of go back to revisiting this R squared. So right now, it might seem like, okay, it's not that much different, right? It'll become a little more complicated down the road, but I'm introducing that idea now, okay? Now, if I look at a second example, so I've got that kind of COVID county data and the percent vaccinated. Well, there is our X variable statistically significant. Well, what levels could I reject that the coefficient is 0 at? With a p-value of 0, I can reject at all levels, right? That's going to be less than any alpha I choose. So I've got a variable that is a good predictor. So should it be able to explain some of the variation in Y? Yes, right? Now here's where it's not quite clear how high R squared is going to be. It's not going to be 0. Here it's only what? 0.04. So this variable of vaccinated, the percent of the county that's vaccinated, how much variation, or kind of in those COVID case, in that Y variable of COVID cases, using the percent of the county that was vaccinated, I can only explain 4.2% of the variation using this one variable. So if you think about anything, if I'm just trying to predict something just using one variable, my R squared is likely going to be pretty low. Right? When we go to kind of multiple linear regression, we think about, well, how can I increase that R squared? How can I explain more of the variation in Y? I can use more variables. But right now, we're just staying at simple linear regression using one variable. So our R squared values are usually going to be pretty low. Okay. Any questions before we keep moving here?
However, like the smaller R squared would be considered like the outlier event, a high R squared.
What's the highest R squared could ever be? Which would mean I'm explaining 100% of the variation, right? So there's no like right or wrong answer. The closer we get to an R squared of 1, the closer we're getting to explaining all of the variation using just that one X variable. Once again, if we're just using one variable, it's likely R squared is going to be a lot closer to 0 than it is to 1, unless we have something like, I don't know, predicting weight by height, or something that they're very, very strongly correlated. Any other questions at this point? Okay. So let's go back to Stata and think about some other things that we could do. All right, so I'm going to scroll back up here. Oh, a little bit too high there. So I'm going to go back and open up that COVID county data again. Okay. I'm going to run that very simple kind of linear regression, or actually, let's go down here. Let's do this one. Okay. So if I'm trying to predict, well, hold on. I want to make another point. Let's do this. All right. So this is the regression we were just looking at, right? So our R squared was 0.042. So the percent of the variation in COVID cases we were explaining with the percent of the county that was vaccinated was only 4.2%. Let's say I try to predict the number of cases instead using household income, right? Well, what percent of the variation in COVID cases was explained by household income? About 10%. So which one of those variables is a better predictor of the number of COVID cases? Well, which one is explaining more of the variation? Income. So here, if I'm trying to make predictions, which of my predictions are going to be more accurate? If I make them using household income in that county instead of the percent of the county that's vaccinated. During COVID, the government would definitely probably, wouldn't like this to be out there, right? Because they were trying to convince people to get the vaccination. While that might impact, right, it was still statistically significant, but the amount of variation explained in the number of COVID cases was much smaller than simply the income in those areas. Why? Because people with higher incomes probably had the likelihood of not working as much, staying at home. They might have had more resources available to them. Avoid being in areas where they were having, they weren't essential workers. They didn't have to go to work, interact with as many people. And so we end up there having household income was a better predictor. Okay. Now, if I scale this variable, right, and I divide it by 1,000. So now instead of dollars, my income variable is going to represent changes in 1,000. The unit is $1,000. Okay. So if I do that, we said kind of last class, what will happen to my coefficient? Well, the effect of $1, how would I get the effect of $1,000? Simply take the effect of 1 and multiply it by 1,000. So what should happen to that coefficient that we found? It should go to what? 0.4 or negative 0.4 instead. Sure enough, we run this regression. I get the same coefficient. I've just scaled it, right? So when I scale my data, I will get a different coefficient because the units have changed. But what's going to happen to my test statistic and p-value? Well, when I change the units, my coefficient units change, but so does my standard error units. So when we create these test statistic, it cancels the units out. So notice what's happened to my test statistic and p-value? Exactly the same. What's going to happen to my R squared? Stays the exact same. R squared is a unitless measure, right? That total variation that we're explaining is in dollars or thousands of dollars. The total variation that actually exists is in dollars or so. So if I divide a dollar by a dollar or $1,000 by 1,000, my units are going to get canceled out. So hopefully I'm not lying to you. What's happened to the R squared? Stayed exactly the same, right? So it doesn't matter when we scale these variables. Nothing's going to change about our rejection decisions or that R squared value. Okay, so that might be questions I could ask like on the quiz or something. Okay. I have kind of another unique example here. So let's do, I'm going to add this in here. Actually, I'll add it up here. Oh, not standard income. I want what? That median household income, right? So if I run this regression, what would be the interpretation of this coefficient? Well, if I have kind of median household income, right? Oh, did I change it to be in thousands? No, great. So this is in dollars, right? So if the median household income in a county goes up by $1, the predicted percent of that county that gets vaccinated would go up by 0.0003. It's a very small effect, but is it statistically significant? Very. P-value is 0, right? So I could reject at all levels. Now, if I instead standardize my income variable, so we talked about this a little bit. How do I standardize a variable so that it represents the number of standard deviations away from the mean? I would take the X variable, I would subtract the mean, and divide by the standard deviation. So if I create the mean of that household income, I create the standard deviation. I then take every observation's value for income. I subtract the mean. Let's get this all in one line. And I divide by the standard deviation. I now have a standardized variable. Well, all I've done is kind of scale that variable just like I did before. So what should happen to my test statistics and p-value? Test statistics and p-values are unitless. the R squared is unitless. So if I'm standardizing a variable, I'm just changing the units, right? So if I were to now run this regression using the standardized value of income, right, I will get different coefficients because the unit now is not a dollar, it's being one standard deviation away from the mean. But in terms of my test statistic, p-value, and R squared, they're exactly the same as before. So scaling variables will change your coefficient size, but it won't change its statistical significance. Okay. Any questions on this idea before we keep moving? I want to show you one more interesting thing that might help on the problem set or the quiz if we standardize a variable. Okay. So if I standardize a variable, so I'll use the example that we just had. So I was trying to predict the percent of a county that was vaccinated using the standardized value of income. Okay. What would the interpretation of my intercept be? So the interpretation of the intercept is the predicted y value if my x variable is equal to 0. If my x variable, if I standardize it, when is it equal to 0? When income is exactly, well, if it's standardized, the unit tells me the number of standard deviations away from the mean. So now it would be an income value that is the mean, right? It's 0 standard deviations away. So what my coefficient is now telling me is if I'm looking at the mean income value, this is the kind of expected value of vaccinated, right? So what this should tell me, right, is essentially when I have an income of the mean, what is the percent of the county that's vaccinated? Or what is the mean y value? So if I go back here, and now we're thinking about this coefficient on the constant, oh, what did I want here? Oh, what did I do? Sorry. What do I want here? Oh no, sorry, this is right. I don't need to add anything in here. All right, this is right. Okay, so sorry. Here is my original regression. That constant was 40.77. I said that should represent the average of that y variable. Sure enough, it's exactly the same. Okay, so we get kind of these weird interpretations if I standardize variables. I could standardize both variables here. It's not going to be ultimately that interesting, but just for the sake of this, if I standardize both variables, notice what value do I get for the constant? Well, if I've standardized both variables, and I said if I standardize the x variable, it gave me the mean of the y variable. If I standardize the y variable, what should the mean now be? If I standardize a variable, the mean will be 0. So what value do I now get for the intercept? Whenever you see these e's, this is essentially like in math when you write times 10 to the whatever power, it means move the decimal that many places. So if it's e and it's a positive value, it means move the decimal that many places to the right. If it's e at a negative value, it means move it that many places to the left. So I basically have a constant here of 0, right? 0.000001. I might have forgot a 0 there as I was saying and lost track, but you get the idea, right? So we can scale variables, and sometimes if we're doing that and standardizing, the interpretations become a little bit weird, right? I would focus less on this, but I just wanted to kind of make the point since we've talked about standardizing variables and when it's getting more kind of familiar with making these actual interpretations. I know what's on the quiz. I know how much time we have left in class. So maybe I'll be friendly again here today. And we'll kind of talk through some of these. It'll allow us to kind of introduce the next topic. So I'm going to have this set to be think we can get through this in the next, what, 9 minutes? So I'll set it to be 135. I'm then going to set the code for today. We won't shuffle the answers for the sake of this class. So I'm going to change this to be 10.20. Now that's today's kind of access code. Now I'll change that later. We don't really need to worry about that. And then I'm going to come down here. I'm going to publish it for us. Okay. So that in-class quiz 3, the code that will get us in is 10.20. We're now going to kind of work through this together. So hopefully everyone gets all these correct if we're paying any modicum amount of attention to what I'm saying. All right. So got quite a few questions here. So the next thing we're going to start talking about is what if I have a variable that is a dummy variable? It's a 1 or a 0. Okay. So if I have the unemployment rate of a county measured in terms of the percent, so the unit is percent, but my Y variable is a 1 or a 0, right? Simply, was that county considered a metro county? 0 if not. So now how do I interpret my slope coefficient? If the unemployment rate goes up by 1%, right? Then the Y variable changes by or goes down by 0.045. What is the units of a dummy variable? Well, I can either see a 0 or a 1. So 0 would mean there's a 0% chance that it's a metro county. 1 would mean it's a 100% chance it is a metro county. So changes going from 0 to 1 are going to be changes in the probability I belong to that one group. So if the percent of a county that's unemployed goes up by 1%, the probability it's considered a metro county goes down by 0.045. If I have a probability, I could also say that it goes down by 4.5%. So in general, we'll kind of keep these in terms of probabilities. So if the unemployment rate goes up by 1%, the probability that it is a metro county would decrease by our coefficient value of 0.045. Okay. So when we have these Y variables that are dummy variables, the units are changes in the probability. Okay. So if instead I come down here, just introducing these ideas, what if instead my independent variable or my X variable is a dummy variable? So here I'm trying to predict whether the number of new COVID cases from whether or not that county was in the South or not. The idea in the South, it's warmer, people are less likely to be cooped up inside around other people, and so maybe there was an effect on the number of cases. Okay. Well, here, if I am thinking about what levels for this variable, it doesn't matter the interpretation, but we can make it here in a second. How would I now interpret my coefficient? What's a unit change in my X variable? If it's a dummy variable, it can only ever go from 0 to 1. So now it would be if I went from a county that was considered not in the South to a county that is in the South, the predicted change in Y, or the predicted change in the number of new cases in that county, would be 892. So this actually had kind of the reverse effect that I initially might have thought intuitively, that when you have a county in the South, it was much more likely, it was warmer, people were out doing more things, and so what happened with the spread of COVID? Went up, right? Is it statistically significant? Well, here we got kind of a tricky one, right? Because what's my p-value? So we make our rejection decisions for dummy variables the exact same way as we did before. All we have to do is look at that p-value in the test statistic. What is my p-value? 0.01. I only reject if that p-value is less than alpha. So is it less than 0.1? Yes, I can reject with 90% confidence. Is it less than 0.05? Yes, so I can reject with 95%. Is it less than 0.01? Just barely not, right? We're right at that point where it's equal. So I would actually say I failed to reject with 99% confidence. So the only levels we can reject at are the 90 and 95% confidence levels. Okay. Any questions on that idea? Just to kind of get at this here, we can kind of spoil the answer, but if I had a smaller sample size, right? In fact, I'll give you the answers here and then we'll talk through them just so we don't have to worry about submission times. So here, question 3, the only answer is R squared. And if we come down here, 4 is the mean crime rate. Okay. We'll talk through this one because we just had an example very similar to it. So let's say I ran this regression where crime rate, so just to be clear before we kind of go into these, you now have the answers to 3 and 4. We talked through the answers to 2 and 1. You should hit submit on the quiz, right? Everyone who is here should get 100% in this quiz today. Okay. So are there any questions before we dive into why the answers for 3 and 4 are correct? Okay. So this is where we want to start getting used to terminology. Let's say I'm instead trying to predict, instead of COVID cases, crime rates. And I want to do that using the unemployment rate of a county. If I standardize that unemployment rate variable, we've said that what is the interpretation now of our intercept? Well, if I standardize, when we talk about the dependent variable, it's what depends on something else. So that is my Y variable. My dependent variable is what I'm trying to predict. Here, it was co-crime rate. My independent variable is the thing that is changing that helps me make these predictions. So my X, or my right-hand side variable, was the unemployment rate, but standardized. So if I'm thinking about my predicted value of Y, what is the intercept's interpretation? It's the predicted value of Y when the X variable is equal to 0. When a standardized X variable is equal to 0, I'm looking at the mean unemployment rate, which should then give me my mean Y value, right? When I'm making my prediction, okay? Because if I standardize it, we're kind of going back to that mean point of the X variable. That should be also the mean of my Y variable. So here, the mean of my Y variable would be that intercept coefficient. Right? Just like the earlier, we had 2 different variables, but we had kind of the same thing going on. Now, what might get a little trickier is what if I had this regression that I ran in 2? So this is where it doesn't matter if we're using dummy variables or not, right? The same changes are going to occur to all of our statistics in terms of our statistical significance. So here I have the same regression, but a smaller sample size. Okay. So what is a smaller sample size going to do, right? If I have a smaller sample size, we said our test statistic, this one's dying on me. That one's dying on me too. There we go. Was that sample coefficient divided by its standard error. But our standard error, we said we could think of it as it's the sum of our errors squared over n minus 2 over something I told you not to worry about, right? So if n is now smaller, what's going to happen to our standard error? And this is how I would work through these problems, right? Don't try to just think of this all in your mind. It's easy to get jumbled. If the denominator is smaller, what happens to this fraction? Goes up. Hopefully we need to understand how fractions, numerators, and denominators work here. If my denominator here in my test statistic is now larger, what's going to happen to my test statistic? It's going to go down. If I only reject when that test statistic is less than an absolute value, my critical value, if this is lower, right? Or sorry, we only reject when it's greater. If my test statistic is now lower, is it going to be more or less likely I can reject? Well, if I only reject when it's greater than my critical value, as it goes down, it becomes less likely it's greater, or less likely I can reject the null. Okay. If my test statistic goes down, we said this is where we can think about. If I have my test statistic, the area to the right of it, if it's positive, area to the left, if it's negative, this would represent half my p-value because we're always doing a two-tailed test. So if my test statistic goes down, what's happening to my p-value? My p-value would be getting What's happening to the area to the right of my test statistic? If the test statistic is smaller, it's going up. If I only reject when that p-value is less than alpha, if the p-value is getting higher, I am less likely to reject. So the things that we'll see kind of happen with this smaller sample size is my test statistic is going to change, right? We said the direction it's going to change just now, but it is going to change. The reason why is because my standard error was changing when I took that smaller sample size. If my test statistic is changing, my test statistic and p-value are directly linked. The higher my test statistic, the lower the p-value. The lower the test statistic in absolute terms, the higher my p-value. So all of those are going to be changing. What about the R squared and adjusted R squared? Well, we haven't quite gotten to talking about the adjusted R squared, so it probably doesn't make sense that that's going to be my answer. We'll kind of talk more about that probably next week. But what is not going to change in theory? It doesn't matter what sample size I have. It's kind of back to that experiment we did with confidence intervals. If I were to take enough samples, and say I had 1,000 different samples, so I end up with 1,000 different R squareds. They should always be centered around whatever that true R squared value is. So from any one sample, we might see a slightly higher or lower R squared. But in theory, if we were to take enough samples, on average, we would get the exact same R squared value. Okay? So the statistic that won't be influenced by our sample size up to this point is going to be that R squared. Our adjusted R squared is going to take into consideration the sample size. So I'm kind of giving you like a little spoiler for next week. There, our adjusted R squared will be impacted by our sample size, but the R squared itself is not. Okay. Any questions over any of those that you want to kind of revisit? And we'll dive deeper into dummy variables here in just a second. Okay. So here we'll start talking about dummy variables. I'll go through this pretty quickly because not a whole lot changes, right? So what are some examples? Really, they're just going to be identifiers. So a lot of the times, like we'll have gender. I know I'm probably not supposed to use that example now, but Riley, if we had a binary, like if you look at a lot of data sets, we have binary records of gender. So if you're looking at like medical records, you're going to have ones and zeros, all right? Maybe I'm looking at, is somebody over 60 or not? So any variable that you would create using a conditional statement, a 1 if the individual is greater than or older than 60, 0 if they're not. That's a dummy variable. What about whether or not it's a student athlete? 1 if they are, 0 if not. Right? These are examples of our dummy variables. Okay. I don't know how they ended up being called dummy variables. There's probably a very good reason. I should probably look it up on Google so I have the answer, but that's the idea. Right? So when I'm running my regression with that dummy variable as my independent variable, the thing that's changing, we said, what's the interpretation now of a unit change in that dummy variable? If it goes from a 0 to a 1, that's the only change we can ever see in a dummy variable in terms of it's the independent. So it's going from the 0 group to the 1 group would impact our predicted y by whatever its coefficient is. Okay. So let's look at this very fast. It's the exact same thing as we were doing before, right? We could do left, we could do right, we could do two-tailed tests. We could assume that that slope coefficient is different values. We're always going to resort to that two-tailed test where we assume that the coefficient is equal to 0. So this would go away. Then it simply becomes taking that taking the estimate we have for the slope coefficient, dividing it by the standard error to get our test statistic. Looks no different than what we were doing before. It's the exact same thing, okay? So in terms of doing our hypothesis test, steps haven't changed at all. Everything's the exact same as what we were doing before, okay? So if I'm looking at some regression output here I was trying to predict college GPAs from whether or not this was a student athlete, okay? So my imagination, I'm not controlling for a lot of other factors, but I was thinking about this last night. The IU basketball team, their game started at 11 p.m. in California, right? They were probably having to travel a lot for that. You think about the football team, they've been doing it. A lot of their time is taken away from being able to study if they have a real major, right? And so if they have less time, if I'm looking at a student athlete, what would I expect if they can't study as much that their GPA is likely going to be lower? So if I run this regression where I'm trying to predict a student's college GPA, and I simply am doing that with a dummy variable, 1 if they're a student athlete, 0 if not. How would I interpret my coefficient? If they're going from not being a student athlete to being a student athlete, their predicted GPA is going to go down by 0.28 points. Okay. Is that a statistically significant effect? Well, with a p-value of 0, highly statistical at every level. In fact, how could I use the confidence interval here to make my rejection decision? Well, the confidence interval tells me the possible values for that slope coefficient. Is 0 one of those possible values? No. So I would be able to reject it with 95% confidence. Okay. Yeah.
Just be clear though, the R squared does mean that very little amount of that.
So even though we have a statistically significant effect, what this would tell us is being a student athlete does have a strong effect, a strong relationship with college GPA. However, there's a lot of other things that probably explain your GPA than just being a student athlete. That's what our R squared is telling us. That being a student athlete, although it is statistically significant and related to your GPA, it's only explaining what? 0.8% of the variation in your GPA. It's likely that your major choice, right? Number of classes, maybe your high school GPA or ACT score, those are likely going to be have a lot higher R squareds, right? So there's still a lot left so if the R squared is the percent or proportion that we can explain, what is 1 minus the R squared? It'd be the proportion that we can't explain. There are likely a lot of other factors that are explaining the variation in GPA that we're not using here. Yep. Say it again. So we haven't dove into multiple linear regression yet. We will eventually, right? So, but you're thinking of it in the right idea. If I could add more variables to make my predictions, my R squared should get higher. Yeah.
So higher R squared means what it does really affect the other.
It means it's explaining a larger proportion or a larger percent of the variation in that Y variable. So I'm making my predictions are likely to be a lot more accurate. Yep. Okay. Any other questions here before we keep moving? All right. So I kind of already went through this, but let's think about, we'll come back to this slide. And I'll use my example that we just looked at to kind of make this point. So if I'm trying to predict GPAs using whether or not they were a student athlete. Okay. My predicted GPA for anyone who is a student athlete would be what? Well, if they are a student athlete, the dummy variable is if they are a student athlete, the dummy variable would be a 1. So what would my prediction be? The estimate I see for the intercept plus the estimate I see on the slope coefficient. So this would be for a student athlete or the 1 group, whatever example we're looking at. Now, what would my predicted GPA be for a non-athlete, or in any other example that we're looking at, the 0 group? Well, there, athlete is a 0. What is my predicted GPA? Simply the intercept. So the intercept is going to tell me what? It's another statistic that this would represent. For every single observation I have, when I make a prediction for the non-athlete's GPA, I'm always going to get the same value. So this is going to end up being the mean of my 0 group, or the mean in this case of the non-student athlete. What will the mean of my 1 group be? Or what would the mean of my athletes be? Beta 0 plus beta 1. Once again, I don't know if we'll have quite enough time today. We could actually do this, right? In fact, we'll kind of see where we get to in the slides, but maybe I'll show you an example before we end class to kind of prove that statement to you, right? So if I'm thinking about this here, the mean of my 0 group, and I think in this case I had height and whether or not they were male, the mean female height would simply be the intercept, and the mean male height would be the intercept plus that dummy variable's coefficient. Okay, very similar to our student athlete GPA, just different variables. Okay. So what would that what would the slope coefficient represent? Basically, it's the difference between that 0 and 1 group's y variable, right? Or the difference in means. Okay. So I think I've got an example here. Let's see if I went through. I didn't. We've kind of already talked through these interpretations. I want to go back to Stata here for the sake of what we've been talking about. And I'm going to go through, since we already had this open, where do we leave off on? We left off right here, right? So I'm going to look at my dummy variable examples. I'm going to come down here and simply run this regression, okay? So once again, this is the number of cases per 1,000 people and a dummy variable for whether or not the county was considered in the South or not. I forget what states this included, but you know, Alabama, Florida, whatever the group was. So if I run this regression, I get that. I got my slope, my intercept coefficient, okay? What should that intercept represent? We said every time I make a prediction for a county that is not in the South, what's the only thing that gets added into that prediction? The intercept. Because every county not in the South, that slope coefficient in the South is getting multiplied by 0. Okay? So this should be the mean kind of number of cases for non-South counties. What would the mean of my South counties be for the number of cases? Should be 33.6 plus 15.48. So about what? Close to 50, right? So if I come down here, we haven't looked at this command yet, but I can do something in Stata where I use this by sort command. So what by sort does, so BYS is what that's short for, it sorts the data, and then by every single value for that variable, it will do whatever you put after this colon. So we're going to be keep it simple in this class for right now. All I want to do is use the by sort command. So I say by this variable South, sort it, then look at all the possible values. Well, if it's a dummy variable, the only possible values are 0 and 1. And for those two groups, summarize this COVID cases variable. So what that would do is take every county that has a 0 or non-South county. When I summarize it, it should tell me the mean. That'll be the mean of those non-South counties. Then by the second group, or the second value for that variable of 1, it'll summarize them and give me the mean of that group, or it should be the mean of my southern counties. Okay? So if I go here and I run this command, I can look at the data. Oh, I clicked the wrong thing. Hold on. I can look at the data and this variable I created. Oh, did I not run it? Hold on. We got too many things going. Oh, here, I got the reported values right here, right? I forgot. I didn't create a variable. I just summarized it, right? I could have created a variable as well and looked at the data set. Here, I just summarized it for you to make this point. When I'm looking at the value of 0, for non-South counties, the mean was 33.66, which is exactly what we said the interpretation of that intercept should be. The mean of the 0 group. Now, what was the mean of all the South counties or the 1 group? 49.14. Sure enough, when I took that intercept plus the slope, I said that should represent the mean of the 1 group, right? Close to 50, right? I didn't do I was rounding in my head when I was doing that math. So that's how we can kind of look at these simple linear regressions with dummy variables. They're really telling me something about the means of those two groups, okay? Now, we'll eventually get to your point earlier, multiple linear regression, and there our dummy variables have slightly different interpretations, right? They won't necessarily just represent means. We'll talk a little bit more about them kind of once we get to that point. Okay. So that was using dummy variables as our independent or our X variable. Okay? And once again, when it goes to making rejection decisions, everything else just stays the same as what we've been doing, right? Because once I get my test statistic, it's unitless, right? So it just goes back to, is the test statistic greater than or equal to the greater than the absolute value of the critical value, we reject. If our p-value is less than alpha, we reject. If 0 is not in our confidence interval, we reject, all right? 3 ways of doing the same thing, okay? Any questions on that before we keep moving? All right. So to kind of got a couple more minutes left here, I want to give you as much as possible to kind of help you with that problem set. So this is where, once again, I think we're going to get a little bit of spillover of dummy variables into Tuesday's class. Probably won't be a lot of time we spend on Tuesday on it. So get started on those problem sets early so you can work through all the questions up to when we start using a dummy variable as our Y variable. Now, we've kind of already talked about it a little bit. You could probably figure it out, honestly, but we probably won't cover all that material until probably the first 20, 30 minutes on Tuesday's class, okay? So you will need that for that first problem set. So let's say this was very similar to the in-class quiz, right? This is the exact same example I used. So just to kind of reiterate, how would I interpret that coefficient? It's always a 1 unit change in my X variable. So if the unemployment rate goes up by 1%, that is the predicted change in my Y variable. We said when my Y variable is a dummy variable, moving between 0 and 1 would be changes in the probability I belong to the 1 group. When I say the one group, the group that is identified using a 1, right? So here, if the unemployment rate goes up by 1%, it still is in units, right? It is not a dummy variable. The predicted probability of the Y variable being a metro county would go down by 0.045. So the coefficient you see when you have a Y variable that's a dummy variable are changes in, can't reiterate this enough, I probably said it a lot, you're probably tired of it, but it's changes in the probability, not percentage, right? We can convert it into a percent by simply multiplying by 100, and that's often, most people talk in percentages and not probabilities. I have no idea why that is, but most people, like, you know, when you say something is more or less likely, you don't usually say, well, the probability of it's happening and goes up by 0.2. Most people would say it goes up by 20%. But they're saying the same thing. You're just scaling it. Okay. So we kind of already talked through that. What would the interpretation of beta 0 be here? Well, it goes back to the same thing. It's the predicted value of Y when my X variable is equal to 0. So the predicted probability, I have a county that's considered metro, when the unemployment rate is 0, would be whatever that interceptor constant is. Or there's about a 60% chance that if I select a county and has an unemployment rate of 0, there's a 60% chance that it's considered a metro county. Okay. Which might be kind of counterintuitive. And you might think metro counties have higher, but here, once again, to kind of getting back, we'll dive into state a little bit more to revisit dummy variables next class. We are only doing simple linear regression right now. I said this class, I was talking with another instructor today who teaches the other section. It gets easy to fall behind because we literally just keep building, right? We will go from simple linear regression, which we might start thinking like, yeah, of course our R squareds are going to be pretty low. We're only using one variable to explain why. So once again, here, how much of variation in being a metro county does the unemployment rate explain? Only a probable portion of it of 0.03, proportion of it of 0.03, so 3%. Well, it's because we're only using one variable. So what do we want to do? We want to use multiple variables to try to make our prediction. That's going to be down the road, right? That'll probably be next Thursday's class. Okay. So we'll kind of revisit dummy variables Tuesday, just using Stata, right? So we've gotten through the slide portion of it. I kind of already showed you a little bit of how we do this in Stata. It's going to be the same thing. You use that REG or that regression command. It's just that your Y variable is a dummy variable. Once you do that, you can obtain the regression results that we've been looking at in the slides. So my guess is you can probably work through the entire problem set. The last 2 or 3 questions, it might help a little bit after seeing what we do the first 20 minutes of Tuesday's class, okay? Then on Tuesday, just to give you some foreshadowing since you have a couple minutes, we'll talk about hetero versus homoscedasticity. It's a weird terminology that we haven't talked about yet, so don't feel like you should have any idea. We haven't touched on anything that's related to that. Well, at least for now, it shouldn't seem like we've touched on anything related to this. Once we finish that up, we're going to move to multiple linear regression. So we'll probably start multiple linear regression toward the end of Tuesday's class and then really focus on it next Thursday. So what I don't want you to do, this is important, so I want you to listen, all right? For that problem set and for that second quiz, I am only expecting you to answer things up through the end of that homo-heteroscedasticity conversation. So we should only be using simple linear regression where we have one variable on the right-hand side. Because that quiz will be open to be due and turned in before the end of the day next Friday, we'll have started talking about multiple linear regression next week. Don't use any of that when it comes to quiz 2. Because when we have multiple linear regression, it starts to complicate some of the things that we've talked about. We kind of have some simplifying assumptions right now when we only use one X variable or one right-hand side variable. That'll change a little bit when we start to add multiple variables. Is that clear what I'm saying? Okay. So other than that, I will kind of get a post as soon as I know what my office hours will look like next Wednesday and I move them. If you do want to meet this Friday, you can send me an email. I'll be around the building most of the day. We could set up a time. Otherwise, have a fun, safe weekend, and I will see you guys on Tuesday.